Hello, everybody. So there was an email about requesting help on the optimization problem. So I've got 3 or 4 examples that we're going to go over. And feel free, obviously, to skip around the video. I hope you're doing that in general. But so first example, just a parabola with a slew of questions. This is a situation where you're given the polynomial and you just have to kind of analyze it. One is the distance, how far, what's the ordered pair on this parabola that's closest to this point? Another example, this looks like the pigeon problem for your homework. So trying to find the biggest possible structure here, the biggest possible box. So in other words, the greatest possible volume that you could construct if you just have a piece of wood. And 2 positive numbers that add up to something and do something else. So that's 4 examples. So just take the liberty to fast forward or rewind to the scene that you want to see. Starting with the situation where you're given a what's it called, a function. So this function is the height function. It is describing the height of the object based on time. So time is the t value, the independent variable. And if you plug in a number for t, it will tell you the range. And the range in this case is the height. So it'll tell you the height of the object. So the powerful thing about equations is usually when you know one thing, you can find the other. So if I know t, the time, I just plug in t and find the height. But if I know height, I can plug in the height for h and then work my way backwards to find out what time is it when for that specific height. But realize the t is being squared, so there's often going to be 2 times for a single height. I'll talk about that actually right now. When will this object be 95 feet in the air? So this describes the height of the function based on time. So I'm going to replace h of t with 95. So I would, in my scratch work, let me get rid of my face. This would be, God bless America. This would be the equation that it's worth writing this down because this reinforces what this equation is telling you. 95 feet in the air. So 95 is h. And you just want to find the t value that would produce that. And you're not going to, I mean, you could do quadratic formula. You could subtract 95 on both sides and do the quadratic formula. The expectation is that you guys can do that perfectly almost every time. But that's a algebra 2 standard. We are just analyzing this function. So we're just going to use technology to do all the work. So I'm going to go to Desmos here. Excuse me. And here is that parabola, negative 16x squared plus 91x plus 12. And I want to know, when does that equal 95? So y is the height of the function that I'm using. Y is the height, the range. Oh, excuse me. So when y is 95, see what I mean? There are 2 x values when y is 95. So the height, if I throw this object in the air, it's going to be 95 feet in the air at 1.14 seconds after I throw it and 4.55 seconds after I throw it. So that would be the answer. When is this in the air? When is this 95 feet in the air? It is 95 feet in the air. Oops. 1.14 seconds and 4.55 seconds after I throw it. Did I remember those numbers correctly? 1.14 and 4.55? Correct. When will this object be 150 feet in the air? Well, let's get rid of 95 and let's just replace this with 150. And what do you say? This will never be 150 feet in the air. Its maximum does not reach 150. So that means 150 is not in the range of this function. And the range of this function is the height of the object. So this object will never be 150 feet in the air. What is the greatest height of this object? Well, the greatest height is clearly not 150. It doesn't even reach 150, so let's just get rid of that right now. The greatest height is 141.39 feet. That is the greatest height, and that occurs at 2.84 seconds after I throw it. So the greatest height is, what is the greatest height? 141 feet? That I forgot already. 141.39 is the greatest height. Lord. That occurs at 2.84 seconds. 2.84 seconds. Voila. Continuing. How long, oops, don't see that. How long was this object in flight? Well, let's go back to the graph. How long was this object in flight? The object was in flight beginning when x is 0, so it began 12 feet in the air. And I must have been standing on a table or something. And then you threw it, it went way up here, and then it came crashing down and it hit the ground at 5.816 seconds. So it was in the air for 5.82 seconds. That is the 0. How long was the object in flight? For 5.82 seconds. And when you're doing this on the test, you are, I'm not sure what we're going to do. Maybe I'm definitely leaning towards letting you use Desmos because it's just a crazy time. But I would like you to take a screenshot of the Desmos thing you're using. I'm not going to take a screenshot now just to save time. At the 3-second mark, what is the object's height? I'm sorry, was the object's height increasing or was it decreasing? Well, don't forget about this formula. This formula tells me the exact height of this object if I know the time. And I know the time. The time is 3 seconds. So if I plug in 3 into t, I discover it's 141. So that means at 3 seconds, it is precisely 141 feet in the air. Wow, that's really close to its maximum height. Well, is it just before it reaches its maximum height or just after? So is it on its way up to meet its maximum, or is it on its way down to the ground? Without even looking at the graph, we can tell, because remember, the maximum height occurs at 2.84 seconds. So at the 3-second mark, it's already past the maximum. So it is on its way down. The object is on its way down at x equals 3 seconds. And let's see. Moving on to this one, what ordered pair on this parabola is closest to this ordered pair? Well, this parabola has literally an infinite amount of ordered pairs, and this seems like an unfair question. Like, how can I possibly compare all those ordered pairs that are on y equals x squared minus 3 to just this single ordered pair? Like if we were in grade school, we would have to get out, we'd have to first graph this perfectly, graph this ordered pair, and then break out our ruler and try to measure all the possible distances. It would be literally impossible. But we have a function that describes the distance between any 2 points. Thank goodness. The distance formula is the square root of one of the x's minus the other x. You square that difference, and then you add the same thing, but just for the y's, the difference between the two y values. And I think in my notes, earlier I did y2 minus y1 and x2 minus x1. It doesn't matter as long as you're consistent throughout the formula. So I started with x1. That means I'm going to start with y1. As long as they're consistent, if I choose -4 to be x1, that I better choose -8 to be y1. I can't mix them up because subtraction is just not commutative. The order does matter. So this is the function I'm using. The distance between these 2 points, well, one of the points is -4, -8. That's the easy one, -4, -8. But the other point is any ordered pair on this parabola. Well, the solution is easier than you think. This ordered pair, this parabola has an infinite amount of ordered pairs, but every ordered pair is an x and a y. So I'll just let x be any x because the domain is all real. So I can let x be any x value. I can just type in x. But the y value depends on x. That's why we call y the dependent variable. Y is whatever x is squared minus 3. So I don't have to figure out what the specific y is. I just know that the y is going to be whatever the x is squared minus 3. So that's what I put in here. And I need parentheses because you are subtracting one thing, y2, but you're replacing it with two things. So that requires parentheses. And be careful and write clearly when you are writing this function because the parentheses are totally critical. If you miss one, you're not going to get the correct answer. So see that this is one y value minus the second y value. And then that difference, that whole difference is being squared. Now, check this out. This expression on the right here, it all depends on one thing. It depends on x. That's the only variable on the entire right side. It depends on one thing, x. So that means I get to change d into, it's actually a function, so I could just call it d of x. So the distance between this point and any point on here will depend on x. And I'm going to graph this and find the smallest possible value. So I reversed that one. So y equals the square root of -4, parentheses, -4 minus x, square that, plus -8 minus parentheses, x squared minus 3, parentheses to close the y value, a second parentheses to close the difference, y minus the y value. So now this outer parentheses is containing y minus y, and that's the thing I need to square. And enter. And I get this. It looks like a parabola, but it isn't. It does look like one, though. Well, maybe it is. I don't know. But all these y values on this parabola, all these y values are all the possible distances between the parabola and the ordered pair. And the smallest y value is 6.29. So that is I had a sneeze, sorry. This y value is the smallest y value. So if you were to graph the parabola and graph that ordered pair, the closest those two things will ever be to each other is 6.29 units. And that occurs when x is negative 0.355. So so the question was, which ordered pair on here? Well, this is not the ordered pair, guys. No. This is the minimum of the distance function. So the smallest distance was 6.29. And that occurs when x was negative 0.355. Well, what's x? Well, you tell me. What's x in this function right here? X was the x value on this parabola. So I know the x value on this parabola that is part of the ordered pair that is closest to this ordered pair. And if I want to find the x and y, on this function, on this parabola that's closest to this, I just need to substitute negative 0.355. Negative 0.355, that's being squared. And then minus 3. Go to my calculator. 0.355. If I square that, I get a positive. And then if you subtract 3, you get negative 2.8. Whoops, 2.87. So the correct answer is negative 0.355, comma, negative 2.87. That is the ordered pair that is closest to the ordered pair on the parabola that's closest to the point -4, -8. And let me just show you this on the, what's it called? This is probably worthwhile to do. The first one was x squared minus 3. That's the parabola. And the ordered pair was -4, -8. So here's my parabola. Here's -4, -8. This parabola has a ton of ordered pairs, but which ordered pair is closest to this? Do you remember the answer? It was negative 0.355, negative 2.87. And check it out. That looks pretty convincing. This ordered pair, not only is it on the parabola, but it is the closest ordered pair on that parabola to this point. Mathematically, we've shown that mathematically. Okay. 2 more to go. This one person asked me. So that just means one person has a question on it, right? You have a piece of wood that that's 5 inches by 5 feet long. So I just drew out a piece of wood, 5 inches, 5 feet long, but I need the same units. So I converted the 5 foot dimension to inches. That's 60 inches. So 60 inches by 5 inches. Now, what am I going to do with this piece of wood? I'm going to cut it up to create this box. So notice the box has kind of like 3 compartments. I could put, whoops, I forgot to, hold on, pay no attention to that man behind the curtain there. Whoop. And yeah. So whatever, I hope you can see this 3-dimensional object that I tried to draw here. So a shoe box, but with 3 compartments. Now, you could cut up this long piece of wood 1,000 different ways to create 1,000 different boxes, but there's only going to be one way that will give you the largest possible box. Now, notice that it's 5 inches high, so that's the dimension of my piece of wood. And I don't know how long this is going to be. It could be really, really long, but that means I wouldn't have a lot of space to make this dimension right here. Whatever I choose to cut this length right here, this wall is the same as this dividing wall, and it's the same as this dividing wall, and it's the same as this wall. So these 4 pieces are identical in shape. And that tells me I need to make 1, 2, 3, 4 cuts to cut this x value to get this wall right here. So I don't know how long it's going to be. I'm just going to kind of eyeball it. I don't know what this distance is. So this is called x. This is x. And those 4 cuts have to be equal because just by the nature of a box, I mean, it's not going to be some weird box that Salvador Dali has created. It's going to be just a rectangular box. So this wall is the identical dimension as this wall, and the dividers are the same dimension. So I need to make these cuts the first thing I'm doing with my saw is making these 4 cuts on my whole long piece of wood. So 1, 2, 3, 4, I've got these 1, 2, 3, 4 walls. Now, but that's not the rest of my box, is it? Because how many more pieces of wood do I need? How many more pieces of wood do I need? I need this facing wall, right? I need the wall behind it. And remember when I put those stars in? Well, what did they hit? They hit a floor underneath here. And they're all equal length. So this wall right here, this side, the back side, and the floor, the bottom side, are all going to be the same size, at least for this problem. So I have this much wood to cut. Knowing that first of all, I need 3 sides, which the pigeon problem in your homework, you only need 2 more sides because of the picture that the pigeons are caged in. But for my box, I've got 3 long sides that I need to cut, and I'm going to make them all the same length. And I only have this much wood left. So knowing that, I need to make 2 more cuts in such a way that all 3 of these are equal length. So here's where we just start thinking a little bit. Knowing that the whole length of the wood is 60 inches, and I already cut off 4x's worth of wood, how long is the remaining piece right here? It is 60 less 4x, or 60 minus 4x. The original wood was 60 inches long, but I already cut off 4 walls, each of x long. So now what I have left? I don't have 60 inches left. I have 60 inches minus the 4 cuts that I took away. And with this remaining piece right here, remember what we have to do with this? We have to cut it so that I have 3 equal pieces. So that means this, how long is this going to be? This is going to be 60 minus 4x divided by 3. That is the length of this thing right here. Because with my saw, I have to cut it 2 more times so that it just is. I have to be very careful with my cuts to make sure that I have 3 equal pieces to finish my construction. So therefore, each of those pieces is a third of what I have left over. And I had 60 minus 4x left over. So this length is 60 minus 4x divided by 3. And now look at what you have. You have a box and you have all 3 dimensions. It's 5 inches high, it's x inches deep, and it's 60 minus 4x over 3 inches long. And that is enough to create a function. So you get to write a function. The volume, depending on x, equals, let's see here, 60 minus 4x over 3 times x times 5. That is the volume of that's the volume of this thing. And let's graph this. So 60 minus 4x. No. Times x times 5. Again, you don't have to simplify it. We're just going to let our calculator do the hard work. Notice 15. If x is 15, the volume is 0. If x is 15, the volume is 0. And I hope that makes sense because remember, x is this. If this is 15, well, that means this is 15, this is 15, this is 15. And 15 plus 15 plus 15 plus 15 is, guess what? It's 60. That would be the entire board, which means you wouldn't have enough to create the other three sides. So your volume, you wouldn't even have a box. So your volume would therefore be 0. That is why when x is 15, the volume is 0. And when x is 0, the volume is 0, because if you don't cut anything, then you don't have these 4 walls, and therefore you don't have a box either. So your domain is everything between 0 and 15. And we just need to find the highest domain. And I've had a real hard time with this mouse. Okay, so here is the greatest y value, which is the volume. And the greatest volume is 375. Oh, my dog is driving me nuts. There's about 16 rabbits underneath my deck, and every time she sees it, she's just going ballistic. You can't catch a single one. It's pretty funny to watch. Okay. So this graph that you see, this blue graph, is what this is. This is the volume graph, and the greatest volume is 375, and that occurs when x is 7.5. Don't forget what x is. X was how much we cut off here. So x is the depth. And it says, what are the dimensions needed to create the largest possible volume? So my dimensions are, let's see, I had to plug in 7.5 into x. And this is the calculator time. So 4 times 7.5 is 30. 60 minus 30 is 30. 30 divided by 3 is 10. So it is 10 inches by 7.5 inches by 5 inches. Those are the dimensions of the box. That produces the greatest volume, which is 375 inches cubed. Ay. Forget it. There it is. Let's see here. Here's the whole page on display. The last problem that we have here, all the work is already displayed for you. You want to find two positive numbers that have a sum of 100. So stop. Two positive numbers that have a sum of 100 is this. A plus B is 100. If that's true, then B equals 100 minus A. But I could also say A equals 100 minus B. All three of these equations are saying the same thing. Continuing, but the product of one and the square root of the other is the maximum. So A is one of those numbers, B is another. So A times the square root of another. And this is just, so I decided to substitute B with 100 minus A. You could substitute A with 100 minus B, and you would still be full credit. But just realize if you do that, you are replacing one thing with two things. So you would need parentheses. You would have to write that as 100 minus B times the square root of B, because you're taking A times B. Well, you're replacing A with two things. So both of those things have to be multiplied by rad B. So that's why you would need those parentheses. But I didn't replace that. I replaced B with 100 minus A. And I don't need parentheses because the square root acts as a grouping symbol. This line is including this whole thing. And I can't graph A because my calculator doesn't know what A is. So I replace A with X. And this is now a function depending on X. I go to Desmos in this case and just graphed this. It got this cool, very cool looking graph. And I want to find out when is this result the maximum, the greatest? Well, it is the greatest right here. The greatest possible result is 384.9. That's the greatest. That occurs when X is 66.667. X in this case was A. Don't forget, we had to find two positive numbers. And I know A is 66.667. So if A is 66.667, I just subtract that from 100 to find B, and I get 33.333. So don't forget to answer the question. That seems like a silly thing to say, but know what the question is asking and answer the question. Everything else is work that supports your answer. It wanted me to find two numbers that add to 100. Bam, I got it. These two. And when I take one and I multiply it by the square root of the other, I know I'm getting the greatest possible result, which happens to be 384.9.